Okay, let's take a look at this next problem we have here. Uh, they ask us to, or they give us the initially uncharged capacitor, charges from a DC source through a resistance. During two time constants, the capacitor voltage increases from 0 to what percentage of voltage of the steady state? Okay, so looking at our equation for the uh, charging and discharging equation. So whereas before we kept using the integrals, 1 over capacitance, 1 over inductance, and then it was from time 1 to time 2, and then we would take the integral of that, and then that's how we would determine the amount of voltage in something. Well, if we have a resistance that's attached to the element, then we can actually use something called a time constant, which is very useful for us. So for a capacitor, the time constant is going to be equal to RC. This is just a natural property of the system. Our equation for charging and discharging, if we have a resistance and a capacitance, is going to be V of C at a time is equal to V of C at infinity plus V of C at 0 minus V of C at infinity e to the minus time divided by tau, which is our time constant. So whereas before in the previous problems, we only had a capacitance or an inductance, we didn't have a resistance element so that we could find a time constant. If we can't find the time constant, we can't use this charging equation. So we know that from the problem statement, time is equal to 2 time constants. All right. But if we look at the equation, we don't actually have values for these. We actually don't have numerical values for the resistance or the capacitance. It just says that we have one of each. But due to this part of the equation, since we know that time is equal to 2 tau, you can replace it with negative 2 tau over tau, and then you effectively cancel out the taus. So you don't even really need to know the resistance or the capacitance for it. You just need to know it's there. So knowing that, let's go ahead and start plugging things in. So we know that V of C at time 0 is equal to 0. They gave that to us in the problem statement. Okay. And we're going from 0% charged to some number percent charge. We just don't know what that is yet. And this is a percentage of the full charge. So percent of full charge. So let's go plug in what we know. If we do V of C at time t is equal to V of C infinity plus 0 minus V of C infinity e to the minus 2 tau over tau. This will simplify down to V of C is equal to V of C infinity minus V of C infinity e to the minus 2. Remember to cancel those out. Okay, so now we're left with effectively this. This is V of C at 2 tau is equal to V of C at infinity 1 minus e to the minus 2. All right, and You might be wondering, well, how do we get the percentage at that point? Well, we still have this little bit here, and we have the infinity value here. So we can actually calculate 1 minus e to the minus 2, and that gives us a value of 0.8646. So we have v of c, we're going to change that back. V of c at 2 tau is going to be equal to 0.8646 v of c at time infinity. We don't actually know what v of c at time infinity is, but we do have this little factor in the front of it. So this is less than 1. And we can actually represent that as a percentage, because we have to remember, at time equal infinity, v of c of t is equal to v of c infinity. And because we're missing that little bit right there, we can say that this is our percentage of the infinity value at 2 time constants. So we are going to be at 86.46% of VC infinity at time is equal to 2 tau. Okay, so that's an example of a problem they have whenever there's no actual given numerical values.